Okay, so let's begin with the running all the examples that I have presented on the whiteboard in the order that in the order I showed them to you in that presentation. Okay, so let's start with the first case. Let's start with all the real eigenvalues cases, right? So let's start with the repelling node. So you'll have to enter, and by the way, we're going to use actually two different plotters, both posted on the Blackboard. So I'm going to use this one first, 2x plus y. So you have to enter the equations in the component form, right? So the matrix was 2, 1, 2, 3. Therefore, the system is 2x plus y, 2 times x plus 3y. And so let's choose a viewing window that is symmetric, minus 4, 4. And then you could see already from the arrows the eigenvector. So remember, they correspond to straight line solutions. I'm going to click on several solutions, obviously, but you can tell by the way the arrows move that this will be the slow direction. So the one corresponding to lambda equals 1, and this one corresponding to lambda equals 4. So the solutions will move almost parallel to the faster one. So let's click on several solutions. So that's a repelling node. And so notice they are almost parallel to the eigenvector corresponding to lambda equals 4. Now, of course, it's hard to click precisely on the eigenvector, so the system is not going to plot it for you, but in between, right here, where I click right now, will be a straight line solution. This is one eigenvector, and the other one, it's the other eigenvector. So that is the repelling node. Let's do the attracting node. So minus 2x plus y, 2 minus 3y. And let's clear the curves. And now the fast direction, if you look at the presentation, remember that the fast eigenvector is 1 minus 2, corresponding to lambda minus 4. So the solutions move towards 0, and they are almost parallel to the eigenvector corresponding to lambda minus 4, because that portion of the solution approaches 0 faster. So that's the attracting node. So let's move on with the saddle example. Well, actually, let's see, what that was the next one, right? So the saddle. I want to make sure I do them in the order I did it in the Lightbox. So the saddle was minus 3, 1. So minus 3x plus y, and minus 4x plus 2y. Again, if you look at the arrows, even before I click on the solutions, you should see what I'm talking about, right? I mean, the eigenvectors are here and here, right? In between solutions for a while, approach 0, 0, and then move away from it. So they will approach 0 along the negative eigenvalue, along the eigenvector corresponding to the negative eigenvalue, which is this one right here, where the arrows point inward towards 0. So that's the saddle, a positive and a negative eigenvalue. Let's look at the star node. So 2 times x, 2 times y. This will have a single eigenvalue, 2 different eigenvectors. Unstable because the single eigenvalue is 2, which is positive. So all vectors are eigenvectors. Therefore, any point you choose, you'll have a straight line solution, moving away from 0. Change the sign of the eigenvalue from 2 to minus 2. You're going to have a star node, but stable this time, right? Solutions approach 0 on straight lines. So a stable star node. Let's move on to the degenerate node, single eigenvalue, single eigenvector. So we have minus 1, 2, minus 1, 3. So minus x plus 2 times y. And minus 2 times x plus 3 times y. So this is the straight line solution, right? So this will be basically, I'm trying to click right now right on the eigenvector itself, right? So a single straight line solution that moves away where the motion is away from 0, because the eigenvalue here, the only eigenvalue is 1, which is positive. So that's the only straight line solution corresponding to the single eigenvector. All other solutions are curved, moving away from the equilibrium point. So unstable node or repelling degenerate node. Again, analogous to the repelling node, but with only one straight line solution because of a single eigenvector. Same thing, but with a negative eigenvalue. Single eigenvalue, single eigenvector, so that the matrix was 1, 2, so x plus 2y minus 2x minus 3y. Here the eigenvector, if you remember, was 1 minus 1. There it is over here. Trying to emphasize it, the straight line solution. All other solutions are curved, but moving towards 0. So we have, again, a degenerate stable node or a degenerate attracting node. So let's move on now with the 0 eigenvalues. Here we might have sometimes errors in the approximation with the 0 eigenvalues. We'll see how it goes. Let's do the single eigenvalue, excuse me, the single 0 eigenvalue and another positive eigenvalue. 2 times x plus y, 4x plus 2y. So in this case, lambda 1, 0, lambda 2 is 4, positive. Okay, so even before I click on solutions, where you see the gap here, where the arrows change directions, that's the line of equilibrium, which remember was 1 minus 2. So now you cannot click precisely on a line, the computer does not detect that. So it will be either an arrow upward or downward, but it's clear that in between there is that neutrally stable line of equilibrium. So if you click on lots of solutions, you should be able to see the gap that the solutions essentially breaks down over there, right, where is the equilibrium line. So if I were to click precisely on that line, there shouldn't be any movement because that's an equilibrium point. All other solutions move on straight lines along the other eigenvector, away from the equilibrium line because the eigenvalue, the non-zero one, is positive. So unstable line of equilibrium. Moving on, we have a line of equilibrium, but now with the other eigenvalue negative. You could see where the arrows meet. The line of equilibrium in that case was 1 minus 2. Yeah, so see here, the algorithm doesn't, no, that's, I think I'm clicking too fast. And then above the line. All other solutions are straight line solutions moving toward the equilibrium line. And in between it's that neutrally stable, not neutrally stable, sorry, it's stable line of equilibrium, right? Because all solutions approach that line. Finally, in the real case, we have the double 0 eigenvalue, minus 2x plus y, minus 4x plus 2y. Here we should see, no, just a second, let me double check. So minus 2x plus y, oh, minus 4x plus 2y, that was the second row. Okay, so here we have to see only parallel lines, right? The line of equilibrium is right in between where the direction changes. So let's click on some of the solutions over here. So right in between here, right here where the direction changes is the line 1, 2 corresponding to the only eigenvector. That's the neutrally stable line of equilibrium because all other solutions move parallel to it. They neither approach nor move toward that line of equilibrium. So that's the classification for the real case. Let's run now the complex cases, all 3 of them. If I remember correctly, I think the 0 real part is one that doesn't show correctly, so we'll see what happens. So x plus y minus 2x plus 3y. This should be the case with positive real part. So you should see an unstable spiral. Remember what I told you in the presentation, that if the alpha is big enough, the divergence is very fast, so you don't see too many spirals, in fact. You should actually make this alpha smaller to really see the motion in a spiraling way. So remember the way to do this, a little trick of the trade, is to scale down the main diagonal. So for example, instead of 1 and 3, let's put 0.1 and 0.3. And that causes the real real part to be much smaller. So as you can see now, I can really see the spiral in motion, right? I mean, the solution moves away from zero in a spiraling way, but slower. So you have more rotations because alpha is smaller. The opposite one, when you have an attracting spiral, we're going to have, let's do the example in the presentation. So minus x plus y minus 2x minus 3y. Attracting spiral, again, alpha is big enough that the convergence to zero is pretty fast, so you don't see too many rotations around zero. Just like before, scale it down, scale down the main diagonal, and that will cause alpha to be small, and you can see now the convergence to zero in a spiraling motion. And finally, the center, when you have zero real part. So let's see, minus x plus y and minus 5x plus y. So this is the part, this is the problem. Pause for a moment here and pay attention. This is the problem with zero real part or zero eigenvalues. Sometimes the algorithms don't detect the correct behavior. So this shows us an unstable spiral, but we know already that this is the case when alpha is zero, so it should be a fully periodic motion, a full loop. So for example, if I do the same with the other plotter, because the other plotter has a better algorithm, approximating algorithm, you will see that the loop is shown clearly, minus x plus y minus 5x plus y. And there you go. Well, almost perfect, right? But because this thickness is not great, it should be a single loop. But you could tell that the behavior is kind of detected, right? I mean, both solutions are periodic, so this is x with respect to t, y with respect to t, and against each other, they move on a closed loop. So neutrally stable point, center, fully periodic solution. I wonder in the previous case if you change the, I'm not sure if it has, some of the plotters sometimes have different numerical algorithms, or what you could do, you could mix h smaller. H, see this, yeah, I mean, it uses the Euler method. Let's see what happens if we actually make h smaller. Let's see if it detects not quite, it still looks like a spiral. Let's see if I can detect, if I use a different numerical method. Let's, Runge-Kutta usually is the most, yeah, there we go. Runge-Kutta is a more sophisticated numerical method than the Euler method. The Euler method is actually what we learned, if you remember, right? So for zero eigenvalues, you really need to be careful to see whether you actually get the correct representation, or maybe there's an error of approximation. So right now you can see that this is the correct picture, right? The center. So it's important to run these examples on your own to get the feeling of what happens, and maybe even other examples not even in this lecture, just to understand the shape of the solution for each case. So that concludes the lecture.